All right, I'm going to do this problem for my homework. It's homework number 5, and it's problem number 1. And what it's asking me to do is, so I'll read the whole problem. It says, how come you rarely get a delta function when computing a Fourier transform? Numerically, it's because your integral is not infinite. And then your data can be thought of the actual data multiplied by a pulse scaled by a so that its amplitude is 1. Okay, so it gives this the function that we're working with. F of x equals cosine. These annoying suggestions. Let's turn them off. Okay. Cosine of k naught times x multiplied by the square pulse function, a square pulse thing, a, where we found that the Fourier transform of that, and then it's written with this fancy f, just write it like that, of this step function of a equals sinc function of k a over 2 with amplitude of 1 over a. So the a in front, right away, just going to logically say that this a in front is just making the amplitude 1, okay? All right, so we're supposed to use the convolution theorem to find the spectrum of the real data of f of x and discuss how does this change the exact result for the Fourier transform of a cosine, okay? Now, so the Fourier transform of a normal cosine are these delta functions, so we'll just go ahead and go into our convolution theorem. So we have a product of two functions, f of x times g of x, and that is the same thing as the convolution, which is denoted by this asterisk, of the Fourier transform of the two functions. And so that's basically all we're going to have to do here. So first of all, the Fourier transform of each of them, let's define them. So the first one, the Fourier transform of this cosine of k naught x is equal to 1/2. Now there's a couple different definitions of this. I'm using the signal or electrical engineering definition of this, which is 1/2 times the delta of k minus k naught plus delta of k plus k naught. Okay, and then the other one we already know. I'll write it again. Yeah, the other one is this one right here. So the other one of the step function of a is sinc k a over 2. That's our definition. So to find the convolution, so f1, let's just write it that way, because why not? Convoluted with f2 is going to be equal this from negative infinity to infinity, 1/2 up front of delta function k plus, well, I'll write minus first. It doesn't matter, but just to keep it consistent, k minus k naught plus k plus k naught, and then that is multiplied by our sinc of k a over 2. This is dk. But what we'll do is we'll make this this is actually not correct. So what we have to do with our convolution theorem, remember, we have to have a shift. So we'll make that shift right now. It's minus infinity to infinity of delta k minus k naught minus, and we're going to use c here, plus delta, so bracket here, because we have to shift it by this c here in order for this to be correct. K plus k naught minus c, sinc, this bracket here, sinc c a over 2 dc. Okay, so now that we've made our shift, now we have our full convolution. We're going to make a u substitution. I'm going to change colors again, and then say u. I'm going to let u be this argument here. And we're going to split this into two integrals. So our first u is going to be equal to k minus k naught minus c. And then we're going to rewrite our first integral. So our first integral is going to be 1/2, and we're going to have a delta of u. One thing to notice, when u goes to infinity, or when c goes to infinity, okay, then we're going to get u equals some number minus some number minus negative infinity. So this u, yeah, you can just kind of cancel the, like, not care about these. It's minusing infinity at negative infinity. So you see, that's going to make this a positive infinity, okay, and this is going to be a negative infinity on top. However, our du is minus dc. So we have another minus here. So I'm going to do this all at once. I hope it doesn't confuse you, but we're going to flip it again and take the minus away. Okay, so there's no minus out front. We flipped it once because of the definition of u, and then we flipped it again because of the minus sign, okay? So then we're going to have sinc of, we got to solve for c, and c you can see is going to be, it's going to be u, it's going to be k minus k naught minus u. K minus k naught minus u. Okay, so this is going to be k minus k naught minus u, all of that times a over 2. Right? Yeah, okay. And that is dc. All right, so now this is just trivial to solve based on properties of deltas and these integrals. I'm not going to go into that definition, but that ends up just being 1/2 sinc of whatever makes this argument 0. So it's going to be, so u must equal k minus k naught for that to be 0, which means this is k minus k naught times a over 2. And that's our first one, okay? So you can see already, you know, we'll write out the other one just to, we're going to let u this time equal this guy, k plus k naught minus c. So we're going to, du is still going to be minus dc, and then c this time is going to be equal to k plus k naught minus u for our second integral, which is this half, okay? So we're going to get 1/2 integral from minus infinity to infinity. I flipped the limits of integration twice again, and that's going to give us this delta of u sinc of k plus k naught minus u times a over 2 dc. And again, that's going to give us 1/2 sinc of k plus k naught times a over 2. So our full answer is 1/2 sinc of k minus k naught a over 2 plus sinc of k plus k naught a over 2. And that is our full answer. And the question is asking how does that change from just a normal Fourier transform of a cosine? If you graph it, this is going to look really bad, but normally you have at your k naughts, you'll have a delta spike. This time we have what's called a sinc lobe, so centered at plus and minus k naught. So if you have 0 here, and then you have some k naught, positive k naught, you're going to have like these lobes like this, centered at k naught, and this is going to be minus k naught. You're going to have another one like this, centered over here. And so that's what it does. And so it basically gets rid of, in my intuition, it seems to get rid of the infinity of the delta function, and it makes it somewhat more manageable. That's probably good with signals and things of that nature. Well, that is the answer. Thank you very much.